Welcome to the solutions to the Electrostatics Problem Set, problems numbers 12 through 16. We start with problem 12. A proton accelerates from rest in a uniform electric field of 640 newtons per coulomb. At some time later, its speed is 1.20 times 10 to the 6 meters per second. A, find the magnitude of the acceleration of the proton. B, how long does it take the proton to reach this speed? C, how far has it moved in that interval? And D, what is its kinetic energy at that later time? This is a nice AP question because it incorporates electrostatics, Newton's second law, kinematics, and kinetic energy concepts all wrapped into the same problem. To solve for the acceleration, we need to know the force. So the force on the proton is going to be equal to E times Q. The charge of the proton, 1.6 times 10 to the 19. The given strength of electric field, 640 newtons per coulomb, gives us a force of 1.02 times 10 to the negative 16 newtons. Now knowing the force, we can use Newton's second law to find the acceleration. The acceleration using F equals ma, so A would be F divided by m, our calculated force divided by the mass of a proton, which is found on our reference table to be 1.67 times 10 to the negative 27 kilograms, gives us an acceleration of 6.11 times 10 to the 10th meters per second squared. We're now going to use that acceleration to do calculations for B and C. Using the definition of acceleration, or V equals VO plus AT. The time would be the final velocity that it attains divided by the acceleration. Substituting and then calculating, we get a time of 1.96 times 10 to the negative 5 seconds. How far it's moved in that interval, we can use V squared equals VO squared plus 2AX. Solving for x, that would be v squared divided by 2a since the initial velocity is 0. We substitute, calculate, and we get a distance traveled of 11.8 meters. Lastly, we want to know the kinetic energy, which is simply a 1/2 mv squared calculation. We substitute the mass of a proton times the velocity squared, and we get 1.20 times 10 to the negative 15 joules. Okay, moving on to problem 13. Asks us to distinguish between electric potential and electric potential energy. Electric potential, V, is a measure of the potential energy per unit charge. While electric potential energy, we will use the symbol UE, equals Q times V, gives the energy of the total charge of Q at a particular location. 14. Suppose you are sitting in a car and a 20 kilovolt power line drops across the car. Should you stay in the car or get out, the power line potential is 20 kilovolts compared to the potential of the ground. Well, I ran across this cute little ditty that will help you with this answer.
If you get caught in the middle of a big open field during a lightning storm, which of the following uniforms would be most likely to keep you safe? A thick wetsuit, a Superman costume, a medieval coat of armor, or your birthday suit? If you answered medieval coat of armor, you might be a little crazy, but you'd also be right. You'd be crazy, of course, because lightning is much more likely to strike metal than rubber, fabric, or bare skin. The reason is that lightning bolts are just long streams of fast-flowing electrons looking for the easiest path from point A to point B, and no everyday material provides an easier path than metal. So why would a material that lures lightning bolts keep you safe during a thunderstorm? Ironically, for the exact same reason it attracts the lightning in the first place. Metal is a great conductor of electricity. Electrons glide so easily over metals that they barely penetrate into the surface. And if an electrical current happens to be moving over a hollow metal container, like a can or a box or even a welded coat of armor, the current won't reach the inside of the container. Physicists call this kind of container a Faraday cage, or in the case of the steel-woven clothing worn by linemen working on high-voltage wires, a Faraday suit. In fact, your car is an everyday example of a Faraday cage, which is why, despite what you may have heard about rubber tires, it's actually the closed metal chassis surrounding you that keeps you safe. It channels lightning around rather than through you. Of course, if you're away from your car and get caught in an open field during a storm, chances are slim that you'll have a medieval coat of armor or high-voltage line suit handy. In that case, whether you're naked or in costume, your body unfortunately happens to be a better electrical conductor than both air and soil, so it provides a great shortcut for traveling current. Stand upright and you're the fastest route for a descending lightning bolt. Lie down and you're the best path for current racing along the ground from a nearby strike. So the best thing to do is crouch low and keep your feet close together. Crouching low is obvious, but similarly important, when your feet are right next to each other, your legs don't make for much of a shortcut for the current to get from A to B. And even if they are the best path for the lightning, when your feet are the only thing touching the ground, then the current will most likely travel up one leg and down the other, missing critical organs like your heart, something these cows couldn't avoid. But actually, the real best thing to do is avoid lightning altogether, and head indoors when you spot a storm on the horizon.
I hope you enjoyed that. Number 15, a proton moves 2 centimeters parallel to a uniform electric field whose strength E equals 200 newtons per coulomb. We want to know how much work is done by the field on the proton, what changes occur in the potential energy of the proton, and what potential difference did the proton move through. For A, the work done by the field on the proton is going to be F delta R cosine theta. In order to use that, we need to know the force. Since E equals F over Q, F equals E times Q, the proton has a charge 1.6 times 10 to the negative 19, multiplied by the strength of the electric field of 200, and we get 3.2 times 10 to the negative 17 newtons. Therefore, the work done, W equals F delta R cosine theta. The force we calculated times the displacement, 2 centimeters is 2 times 10 to the negative 2 meters. And it says that the work is done by the field on the proton. So the angle between the force and the displacement is 0 degrees, and the cosine of 0 is 1. This gives a work done of 6.4 times 10 to the negative 19 joules. The next question asks, what change occurs in the potential energy of the proton? Well, this answer depends on whether or not the proton is going with the field or is it going against the electric field. If it's going with the electric field, then there would be a decrease in electric potential energy. If it's going against the electric field, there would be an increase in electric potential energy. This question in A asks how much work is done by the field. That means the proton is moving with the field. The field is doing the work, so that means the proton is moving away from the positive towards the negative, and that means there is a decrease in electric potential energy. Now applying that to C, delta V is going to be delta U E over Q. Delta U E, the change in electric potential energy, final minus initial, means there is a decrease in that electric potential energy, and that decrease is indicated by a negative value. So the work done caused a decrease in the electric potential energy, 6.4 times 10 to the negative 19, divide by the charge of the proton itself, and we get negative 4.0 volts of change in potential, which is also called potential difference. In problem 16, we find the electric potential 1 centimeter for a proton, and B, what is the electric potential difference between 2 points that are 1 centimeter and 2 centimeters from a proton? Well, the potential at 1 centimeter is given by V equals KQ over R. K, 9 times 10 to the 9th. Q, 1.6 times 10 to the negative 19. And 1 centimeter, 10 to the negative 2 meters. We do the math dividing by the distance. And we get 1.44 times 10 to the negative 7 volts. The potential at 2 centimeters is going to be KQ over R again, except this time R is 2 times 10 to the negative 2 meters. This makes sense. This would give us half the potential. 0.72 times 10 to the negative 7. You probably have it as 7.2 times 10 to the negative 8 volts. Now the potential difference is therefore going to be final minus initial, or the second state minus the first state. So that would be 0.72 times 10 to the negative 7 minus 1.44 times 10 to the negative 7. That gives us a negative 7.2 times 10 to the negative 8 volts. That will be the potential difference, or the change in potential. All right, more work with electric potential energy and electric potential as we work on problems 17 and 18 in class tomorrow.